Elastic regression won't help you to sing in tune, but if you do it in R, it's not that hard. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about Ridge, Lasso, and Elastic-Net Regression in R. Note: this StatQuest assumes you're already familiar with the concepts behind Ridge, Lasso, and Elastic-Net Regression. If not, check out the quests. To do Ridge, Lasso, and Elastic-Net Regression in R, we will use the GLMnet library. The GLM part of GLMnet stands for Generalized Linear Models, which means that this tool can be applied to linear regression and logistic regression, as well as a few other models. The net part of GLMnet is from Elastic-Net. At least I'm pretty sure that's where it's from. If you know otherwise, put it in the comments below. In the StatQuest on Elastic-Net Regression, we talked about how the Elastic-Net combines the Lasso regression penalty, yeehaw, with the Ridge regression penalty, brr, and that you can control how much either penalty is included by adjusting lambda sub 1 or lambda sub 2. However, GLMnet does things just a little differently. Instead of two different lambdas, GLMnet has a single lambda and another parameter called alpha. Alpha can be any value from 0 to 1. When alpha equals 0, then the whole lasso penalty goes to 0 and goes away. And we're left with just the ridge regression penalty. And the whole thing reduces to ridge regression, brr. When alpha equals 1, then the whole ridge penalty goes to 0 and goes away. And we're left with just the lasso regression penalty. And the whole thing reduces to lasso regression. Yeehaw! And when alpha is between 0 and 1, we get a mixture of the two penalties that does a better job shrinking correlated variables than either lasso or ridge does on their own. Lambda controls how much of the penalty to apply to the regression. When lambda equals 0, then the whole penalty goes away and we're just doing standard least squares for linear regression, or maximum likelihood for logistic regression. And when lambda is greater than 0, then the Elastic-Net penalty kicks in and we start shrinking parameter estimates. Thus, when we use the GLMnet package to do Elastic-Net regression, we will test different values for lambda and alpha. Now that we know how GLMnet works, let's do Ridge, Lasso, and Elastic-Net regression in R. Note: the following code is based on an example written by Josh Day. However, the modified code that I'm about to present can be found by following the link in the description below. First, load the GLMnet library. Then set a seed for the random number generator so that you'll get the same results as me. Now let's make up a dataset that we can use to test out Ridge, Lasso, and Elastic-Net regression. The made-up dataset will have n equals 1,000 samples, and p equals 5,000 parameters to estimate. However, only 15 of those parameters will help us predict the outcome. The remaining 4,985 parameters will just be random noise. Now we create a matrix called X that is full of randomly generated data. The matrix has 1,000 rows, since n equals 1,000, and 5,000 columns, since p equals 5,000. And the values in the matrix come from a standard normal distribution, with mean equals 0 and standard deviation equals 1. And we'll need n times p, or 1,000 times 5,000 equals 5 million, values, since our matrix has n rows and p columns. Now we create a vector of values called y that we will try to predict with the data in X. This call to apply will return a vector of 1,000 values that are the sums of the first 15 columns in X, since X has 1,000 rows. This is what isolates columns 1 through 15 from X, and this 1 specifies that we want to perform a function on each row of the data that we've isolated from X. And sum is the function we want to apply to each row. To summarize, this call to apply will return a vector of values that depend on the first 15 columns in X. Once we have that vector of sums, we add a little bit of noise using the rnorm function, which, in this case, returns 1,000 random values from a standard normal distribution. So this whole thing creates a vector called y that is dependent on the first 15 columns in X, plus a little noise to make things interesting. Thus, X is a matrix of data that we will use Ridge, Lasso, and Elastic-Net Regression to predict the values in y. Bam! Now we need to divide the data into training and testing sets. So we make a vector of indexes called train_rows that contains the row numbers of the rows that will be in the training set. The sample function randomly selects numbers between 1 and n, the number of rows in our dataset. And it will select 0.66 times n row numbers. In other words, 2/3 of the data will be in the training set. Now that we have the indexes for the rows in the training set in train_rows, we can make a new matrix, x.train, that just contains the training data. And we can make a testing set, x.test, that contains the remaining rows. This is done by putting a negative sign in front of train_rows when we select rows from X. Now we select the training values in y and save them in y.train. And we select the testing values in y and save them in y.test. Hooray! We've created our training and testing datasets. We'll apply Ridge, Lasso, and Elastic-Net Regression separately to these datasets so that we can see how it's done and see which method works best. We'll start with Ridge regression. The first thing we need to do is fit a model to the training data. We do this with the cv.glmnet function. The cv part means we want to use cross-validation to obtain the optimal values for lambda. By default, cv.glmnet uses 10-fold cross-validation. The first two parameters specify the training sets. In this case, we want to use xtrain to predict ytrain. Note, unlike the lm or glm functions, cv.glmnet does not accept formula notation. X and y must be passed in separately. Type.measure is how the cross-validation will be evaluated. And it is set to MSE, which stands for mean squared error. Mean squared error is just the sum of the squared residuals divided by the sample size. Note, if we are applying elastic-net regression to logistic regression, then we would set this to deviance. Since we are starting with ridge regression, we set alpha to 0. Lastly, we set family to Gaussian. This tells GLMnet that we are doing linear regression. Note, if we were doing logistic regression, we would set this to binomial. Altogether, this call to cv.glmnet will fit a linear regression with a ridge regression penalty using 10-fold cross-validation to find optimal values for lambda. And the fit model, along with optimal values for lambda, is saved as alpha0.fit, which will help us remember that we set alpha to 0 for ridge regression. Now we will use the predict function to apply alpha0.fit to the testing data. The first parameter is a fitted model. In this case, it's alpha0.fit. S, which I think stands for size, as in the size of the penalty, is set to one of the optimal values for lambda stored in alpha0.fit. In this example, we're setting s to lambda.1se. Lambda.1se is the value for lambda stored in alpha0.fit that resulted in the simplest model, i.e., the model with the fewest non-zero parameters, and was within one standard error of the lambda that had the smallest sum. Note: alternatively, we could set s to lambda.min, which would be the lambda that resulted in the smallest sum. However, in this example, we will use lambda.1se because, in a statistical sense, it is indistinguishable from lambda.min, but it results in a model with fewer parameters. Wait a minute. I thought only Lasso and Elastic-Net Regression could eliminate parameters. What's going on? Since we will compare Ridge to Lasso and Elastic-Net Regression, we will use lambda.1se for all three cases to be consistent. Lastly, we set new x to the testing dataset, x.test. And we save the predicted values as alpha0.predicted. Now we calculate the mean squared error of the difference between the true values, stored in y.test, and the predicted values, stored in alpha0.predicted. And we get 14.47 something something. Bam! Now let's try lasso regression with the same training and testing datasets. Just like before, we call cv.glmnet to fit a linear regression using tenfold cross-validation to determine optimal values for lambda. Only this time, we set alpha to 1. And we will store the model and the optimal values for lambda in alpha1.fit to remind us that we set alpha to 1. Then we call the predict function just like before. Only this time we pass in alpha1.fit and save the results as alpha1.predicted. Then we calculate the mean squared error, and we get 1.19 something something. 1.19 something something is way smaller than 14.47 something something, so lasso regression is much better with this data than ridge regression. Double bam! Now let's see how well Elastic-Net Regression, which combines both ridge and lasso penalties, performs. Just like before, we call cv.glmnet to determine optimal values for lambda. Only this time we set alpha to 0.5. And we store the model and the optimal values for lambda in alpha 0.5.fit to remind us that we set alpha to 0.5. Then we call the predict function with alpha 0.5.fit and calculate the mean squared error. And we get 1.24 something something. This is slightly larger than the 1.19 something something we got with lasso regression. So far, lasso wins. Yeehaw! But to really know if lasso wins, we need to try a lot of different values for alpha. To try a bunch of values for alpha, we'll start by making an empty list called list of fits that will store a bunch of Elastic-Net Regression fits. Then we use a for loop to try different values for alpha. In this for loop, I will be integer values from 0 to 10. First, we paste together a name for the Elastic-Net fit that we are going to create. For example, when I equals 0, then fit.name will be alpha0, because alpha will be pasted to 0 divided by 10, which equals 0. When I equals 1, then fit.name will be alpha 0.1, because alpha will be pasted to 1 divided by 10, which equals 0.1. Here's where we create the Elastic-Net fit using the cv.glmnet function. Everything is the same as before, except where we set alpha. When I equals 0, then alpha will be 0 and result in ridge regression. And when I equals 1, then alpha will be 0.1, etc., 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 until I equals 10 and alpha equals 1, resulting in lasso regression. Each fit will be stored in list of fits under the name we stored in fit.name. Now we are ready to calculate the mean squared errors for each fit with the testing dataset. We'll start by creating an empty data frame called results that will store the mean squared errors and a few other things. Then we'll use another for loop to predict values using the testing dataset to calculate the mean squared errors. Just like before, the for loop goes from 0 to 10. And just like before, we'll create a variable called fit.name that contains the name of the Elastic-Net Regression fit. However, this time we'll use the predict function to predict values with x.test, the testing data. We use the list of fits list and fit.name to pass a specific fit to the predict function, and to pass the lambda.1se value for s. The predicted values are stored in a variable called predicted, and then used to calculate the mean squared error for the fit. Then we store the value for alpha, the mean squared error, and the name of the fit in a temporary data frame called temp. And we use the rbind function to append temp to the bottom row of the results data frame. After we run the for loop, we can print out the results. The first column has the values for alpha, ranging from 0 to 1. The second column has the mean squared errors. Note, these are slightly different from what we got before because the parameter values, prior to regularization and optimization, are randomly initialized. Thus, this is another good reason to use set.seed to ensure consistent results. And in the last column, we have the name of the fit. The fit, where alpha equals 1, is still the best, so lasso regression is the best method to use with this data. Triple bam! Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, well, consider buying one or two of my original songs. Alright, until next time, quest on!